Pulse noise is crucial in modern electronics, especially with digital systems and pulse switching mode power supplies. Understanding the spectrum of pulses helps in analyzing conducted and radiated emissions, which are often specified in the frequency domain. Tools like the Rode and Schwartz spectrum analyzer are essential for this analysis, ensuring compliance with electromagnetic interference specifications. Analyzing pulse noise is crucial due to the prevalence of digital electronics and pulsed switching mode power supplies. Many electromagnetic interference specifications, particularly conducted and radiated emissions, are defined in the frequency domain. Understanding these aspects helps in designing compliant and efficient electronic systems. The spectrum of a repetitive pulse is characterized by its frequency components and amplitude, measured in decibels. Understanding this spectrum is crucial for analyzing how pulsed signals interact with electronic systems, particularly in digital electronics and power supplies. This analysis helps in managing electromagnetic interference, ensuring compliance with frequency domain specifications.
The spectrum of a repetitive pulse is characterized by its frequency components and amplitude, measured in decibels. Understanding this spectrum is crucial for analyzing how pulsed signals interact with electronic systems, particularly in digital electronics and power supplies. This analysis helps in managing electromagnetic interference, ensuring compliance with frequency domain specifications.
The harmonic series of a sawtooth wave is characterized by its fundamental frequency and all integer multiples of this frequency. Each harmonic's amplitude decreases proportionally to its harmonic number, creating a rich spectrum. This property makes sawtooth waves ideal for synthesizing complex sounds in audio applications. The pulse spectrum is characterized by the sync function VF equals A, D, sync DFP, where A is amplitude and D is pulse width. The sync function, sin x, describes how the pulse's frequency components diminish with increasing frequency, crucial for understanding signal bandwidth and spectral efficiency. Analyzing the spectrum density amplitude in decibels, we observe the trapezoidal pulse with V or 3.3 V, d bar 1 microsecond, and TR 0.1 nanosecond. The log amplitude, expressed as 20 log 10 V, shows a range from 160 to 100 dBV/Hz across frequencies from 10^4 to 10^8 Hz. This highlights the pulse's spectral characteristics. The calculated spectrum of a trapezoidal pulse with a peak voltage of 3.3 volts, duration of 1 microsecond, and rise time of 0.1 nanoseconds shows a spectrum density amplitude ranging from 2 to 7x 10^6 volts per hertz across frequencies from 10^4 to 10^8 hertz. This data highlights the pulse's frequency response characteristics. The absolute amplitude of the spectrum for a trapezoidal pulse with V free 3.3 VIV, duration d bar 1 microsecond, and rise time tr 0.1 nanosecond is analyzed. The spectrum density amplitude, measured in VHs, varies across frequencies from 10^4 to 10^8 Hz, providing insights into the pulse's frequency characteristics.
The Fourier transform of a rectangular pulse is crucial in signal processing. It is expressed as G f equals a asterisk sync d asterisk f, where sync x equals sin x / x. This transform reveals the frequency component of the pulse, showing how the pulse's width affects its spectral content, with narrower pulses having broader spectra.
In practical EMC spectral analysis, the voltage spectrum VF is defined by VF darsh AD at low frequencies, where sin x darsh x equals 1. At high frequencies, VF simplifies to APF as sin x reaches its maximum of 1. This relationship is crucial for understanding the behavior of trapezoidal pulse spectra across different frequency ranges. The spectrum of a trapezoidal pulse with V3.3V, d/1 microsecond, and TR 0.1 nanosecond shows a density amplitude ranging from 160 to 100 dBV/Hz. This spectrum is crucial for understanding signal integrity and electromagnetic compatibility in high-frequency applications. The envelope of a trapezoidal data pulse spectrum is characterized by its amplitude, A, pulse duration, D, and rise time, TR. The spectrum density is influenced by these parameters, affecting the signal's frequency response. Understanding these relationships is crucial for analyzing signal integrity and electromagnetic compatibility in electronic systems. The practical electromagnetic compatibility spectrum of a data pulse is characterized by its frequency response, where amplitude is expressed in decibels, volts per hertz. The spectrum shows a 20 decibels per decade slope at 2A pf and a 40 decibels per decade slope at 2A p2 tar. Key parameters include 1PD and 1PTR, crucial for understanding signal behavior. The spectrum of a trapezoidal data pulse is characterized by its distinct frequency components. The pulse's rise and fall times significantly influence the spectral distribution, with sharper transitions leading to broader frequency content. Understanding this spectrum is crucial for effective electromagnetic compatibility analysis, as it impacts signal integrity and potential interference with other systems. Signal coupling to input-output cables can cause interference, affecting clock signals and microprocessor operations. Understanding the mechanisms of coupling, such as capacitive and inductive coupling, is crucial. Effective shielding and grounding techniques can mitigate these issues, ensuring signal integrity and reliable system performance. The envelope of a clock pulse train spectrum is defined by its Fourier series, representing discrete frequencies. The amplitude, A, and time variables, D and TR, are crucial in determining the spectral characteristics. This series is essential for understanding how clock signals propagate and interact with other components in electronic systems. The envelope of a clock pulse train spectrum is characterized by its amplitude, expressed in decibels, and frequency on a logarithmic scale. The clock frequency, F0, is defined as 1/1t. The amplitude decreases at a rate of 20 decibels decade initially, then 40 decibels decade, influenced by the Fourier series of discrete frequencies. A clock signal can be decomposed into its Fourier components, where each harmonic is a multiple of the fundamental frequency, F0. The amplitude of each harmonic is determined by the Fourier coefficients, which are influenced by the signal's time domain characteristics. This decomposition is crucial for understanding signal behavior in frequency domain analysis. In spectrum measurement, V data represents the voltage spectrum of data signals, expressed as V hertz multiplied by bandwidth, BW. V clock denotes the voltage spectrum of clock signals. Clock harmonics are crucial with bandwidths BW1, BW2, and BW3, where BW1 is greater than BW2, which is greater than BW3. Understanding these relationships is essential for accurate signal analysis. The RNS FPC 1500 spectrum analyzer, with a bandwidth of 3 MHz, is crucial for precise signal analysis. It measures power levels from 30 decibel milliwatts to 50 decibel milliwatts, providing detailed insights into signal strength. This tool is essential for professionals needing accurate frequency and amplitude measurements, as highlighted in the review on buldengineer.com. Analyzing the spectrum with a 1 Hz bandwidth reveals signal levels from 30 decibel milliwatts to 90 decibel milliwatts. This detailed resolution allows for precise identification of signal components, crucial for understanding signal behavior and interference. Such granularity is essential for applications requiring meticulous frequency analysis, ensuring accurate signal characterization and effective troubleshooting. Pulse spectra analysis reveals 3 segments in the log amplitude and frequency plane: low frequency up to F1, defined by pulse width, medium frequency up to F2, defined by rise time, and high frequency above F2. Clock spectra include harmonics with amplitude unaffected by measurement bandwidth. The rise time segment of the spectrum often leads to electromagnetic compatibility emission standard failures. To control electromagnetic interference, reduce high-frequency spectrum by lowering amplitude with low-power devices and increasing rise time using low slew rate technology. Pulse duration remains constant. Isolate clock and data traces from input-output traces for effective electromagnetic interference management.